Hello, everybody, and welcome to the second of two press conferences at the 55th annual meeting of the American Astronomical Society's Division for Planetary Sciences, or DPS, which this year is co-convening its meeting with the Europlanet Science Congress, or EPSC. I'm Dr. Teddy Kareta, the DPS press officer, and I'm joined by the AAS's press officer, Dr. Susanna Kohler, as well as Dr. Carrie Hensley and Ben Cassis. Today, we're going to have four speakers presenting a summary of their work to you, the press. Before we get started, I'd like to lay out some sort of ground rules and expectations for how the press conference will go. First and foremost, today's speakers have taken time out of their busy week at this conference to present some of their exciting work to you. And this took significant time and effort preparing on their parts. Please treat all the speakers and their topics with respect, regardless of their career stage, their gender, their appearance, their national origin, or any other attributes. They're doing this for you. And, it took work and effort on their parts to do so. Second, each of the topics today, while they are linked, they are of equal importance to the DPS and the EPSC. We would like to see this reflected in an approximately equal amount of time spent discussing each of today's speakers' talks in the Q&A. Speaking of which, each of the speakers is going to have about 9 to 10 minutes for their talk today, and we will do questions after all of the talks are complete. If you're watching live on this Zoom call, the way to ask questions is the Q&A box on Zoom. After all four talks are complete, I will read them out verbally, and the speakers will answer them verbally for the benefit of people watching later or asynchronously, right? I will mention this again at the end, but if you are interested in reaching out to any of today's speakers, you can reach out to me personally, and I will put you in contact with them. My email is on the DPS website in a bunch of different places. It's on the press advisory, but I'm also going to put it in the Zoom chat right now. I used to be so quick with this, but give me 1 second. I want to thank each and every one of you for actually attending this press conference today. Maybe you're watching it remotely. Maybe you're watching it, weeks from now. We want to appreciate the fact that all of you have taken time out of your schedules to watch this too. And, I want to say thank you again for helping the public understand and, become, aware of all the important and exciting work that the members of the Division for Planetary Sciences and the Europlanet Science Congress are doing. Now, on to today's first talk by Dr. Lynnae C. Quick from NASA Goddard Space Flight Center. Lynnae, you can get ready to share your screen. The title of Lynnae's talk is Cold Ocean Planets, Super Earths or Super-Europas. I think it's going to be an extremely exciting talk. And with that, Lynnae, the floor is yours.
Sure. Thank you so much, Teddy. So I'm so excited to talk about this today. And these are new results, brand spanking new. First, let's think about cold ocean planets, which why are they important and why are they important for habitability? Well, back in 2020, I led a group that constrained internal heating rates and the likelihood for geologic activity on 53 Earth-sized terrestrial exoplanets. So these exoplanets had been categorized as being very much Earth-like. However, we found that a significant percentage of these planets are likely to be ice-covered worlds with icy surfaces and internal oceans. And these worlds may exhibit cryovolcanic activity in the form of geyser-like plumes, similar to what we've seen at the south poles of Europa and Enceladus, and we believe they may have internal structures similar to these icy moons. And this is important for habitability because telescopic detection of this type of geyser-like activity, regardless of distance from their host stars, could indicate that these cold ocean planets have subsurface oceans, they have geological activity that cycles liquid water and energy throughout. Those are two of the necessary ingredients for life. And so they have potentially habitable environments and astrobiological significance. So in our study that I'll be talking about today, we considered 17 Earth-sized exoplanets that we believe may be ice-covered ocean worlds. This includes the outer TRAPPIST planets, Proxima Centauri b, and several planets that were discovered by the Kepler telescope. Many of these planets from past reports in the literature had poorly constrained surface temperatures, and their cryovolcanic outgassing rates in terms of the mass of water vapor that geyser-like plumes might expel from them were not explored. So so we've constrained the surface temperatures of these cold ocean planets, the depths to their subsurface ocean, so how far beneath an ice shell, and their cryovolcanic outgassing rates from these geyser-like plume eruptions. And so before we did all of that, though, we had to consider the total internal heating that these planets receive. So I went one slide too far, but we'll go back. And when we're thinking about total internal heating, the first thing that we want to consider is tidal heating. And this is an image of Europa, and it's being pushed and pulled and tugged by Jupiter as it orbits it. And that gravitational push and pull creates heat in its interior. And we believe that these planets experience the same gravitational tug from their host stars that produces heat in their interiors. And we're able to use a simple equation to obtain tidal heating rates for each planet. The second part of the total internal heating rates that we must consider is the radiogenic heating. And so this is caused by the decay of radioactive elements in planetary interiors. And it's tricky to constrain because it's a function of planet mass and age. But back in 2014, Elizabeth Frank's group published a paper where they provided radiogenic heating rates for Earth-sized planets as a function of their mass and as a function of their age. So we were able to take that and use those values for our planets. And so here are our results. We constrain the total internal heating rate, which is the sum of the tidal heating rate and radiogenic heating for these planets. Here are all 17 of our planets, and we find that all have internal heating rates that exceed Europa's. Several have internal heating rates that exceed Eo's. When we look at Proxima Centauri b, that's especially the case. But both Europa and Io, we know, have internal liquid layers. And so we're confident based on these results and the total amount of heating that they receive that even if these planets have ice-covered surfaces, they have internal water layers. We believe that these are internal oceans. So after we have their tidal heating rates, the next thing that we want to make sure that we constrain is their surface temperatures to ensure that they are actually ice covered. And the reason that we looked again at this is that estimated surface temperatures for many of these planets in the literature assumed dark surfaces with no reflectivity or low albedo surfaces, which is not consistent with ocean worlds. They would have much brighter surfaces. So we investigated surface temperatures for these planets, assuming that their surfaces were as reflective as the ocean worlds in our solar system. We used the albedo or the reflectivity of Earth, Europa, and Enceladus' surface as comparative baselines. We can see that of those, Earth has the lowest reflectivity or albedo, and Enceladus has the greatest. And so we used Europa as, again, a conservative baseline from which to get our results. And in doing so, what we found was that the temperatures of many of these planets were much lower than was originally reported in the literature. You can see on the right, we have 3 columns where we have 5 of our planets. And then in the middle, we have their surface temperature as reported in the literature in the past, and the surface temperatures that we obtained when we assumed that the surface is at least as reflective as Europa. And we found that the surface temperatures are up to, in some cases, 55 degrees less than cited in previous literature. I want to note that Earth's average surface effective surface temperature is 255 kelvins. Europa's is 100 kelvins. And so all of these planets, if we look at the column to the right, fall in between those numbers. And so we're confident that these exoplanets in our study have icy surfaces. If we look at TRAPPIST-1H, I mean, it's about at 144 Kelvin. So that's really, all of these are really an icy surface. And so that's really exciting. So we know how much total internal heating they have. We're confident because of that heating, they have subsurface oceans. We're confident based on our calculations of their temperatures that they have icy surfaces. And so the next thing that we want to consider is how far beneath the surface will these oceans lie? Remember, we have icy surfaces, so we believe that there are ice shells, external ice shells on these planets. We know there's tidal and radiogenic heating that will prevent the oceans beneath from freezing. But we know that ice shell thickness is a function of planet size, surface temperature, and total internal heating. And we see this image on the right of Europa's interior structure with the ice shell or ice covering the subsurface ocean and then the rocky interior. So when we look at we use our equations that allows us to obtain ice shell thickness. These are our results. Here are our depths to subsurface oceans for several of these planets compared to Earth and Europa. If we look on the left, the depth to Earth's ocean is 0 miles. It's right at the surface. All the way to the right, we have Europa, and then we have MOAA 2007 BLG 192 LB, which has an ocean that's 24 miles beneath its surface. So the farther we go to the right, the farther the oceans are from the surface. The more we are to the left, the closer they are to the surface. And I'll just point out, Proxima Centauri b, which has an ocean that's very close to the surface, not even 1/10 of a mile from the surface. And again, MOAA 2007 BLG 192 LB, which has an ocean that's beneath an ice shell that's thicker than the ice shell on Europa. So we know the depth of subsurface oceans, the surface temperatures, and so now we want to think about outgassing rates for these planets. If they have cryovolcanic activity in the form of geyser-like plumes, similar to what the Hubble Space Telescope has detected at the south pole of Europa, and similar to what Cassini has seen at the south pole of Enceladus. So we believe that eruptions of Europa's geyser-like plumes may be facilitated by tidal forces from Jupiter, by that pushing and pulling as it orbits Jupiter that we showed on one of the past slides. And so we think that geyser-like plume eruptions on these planets may be driven similarly by tidal forces, but from their host stars. And so we can use outgassing rates from Europa's plumes as a conservative baseline to explore plume outgassing rates on the cold ocean planets that we considered here. And so here are a couple of our planets. I could not put them all on here, but notice that we have Europa in the center with a water vapor outgassing rate of 2,000 kilograms per second that its south polar plumes expel. And the farther we go to the left, we have negligible outgassing as far as planets. The farther we go to the right, you see on the right side of the screen, we have substantial outgassing. We see for example, on the left, Kepler 441b has very minimal outgassing, 8 kilograms per second. And so again, thinking about Europa as our baseline, we see that GJ514b has almost an equivalent outgassing rates. TRAPPIST-1F exceeds Europa's outgassing rates as far as the water vapor that would be expelled by geyser-like plumes by an order of magnitude. But check out LHS 1140b and Proxima Centauri b. They greatly exceed the mass of water vapor that would be erupted from geyser-like plumes on these planets as they orbit their host stars, greatly exceeds that of Europa's by 2 to 3 orders of magnitude. And just a reminder that these planets also have very thin ice shells. So that means that not only will there be geyser-like eruptions, but the eruptions are likely to issue directly from their subsurface oceans because LHS 1140b has an ice shell that's only 1 mile thick. The ocean is 1 mile beneath the surface. In Proxima Centauri b, the ocean is less than 1/10 of a mile beneath the surface. So here are our conclusions. These cold ocean planets that we've studied are astrobiologically significant. They show that worlds, no matter their distance from their host star, if they are ice covered, they may still have geological activity that cycles the necessary ingredients for life. LHS 1140b and Proxima Centauri b are where we're likely to detect cryovolcanic eruptions in the form of geyser-like plumes, and that can tell us indirectly that these planets have oceans and energy which are needed for life. And there are several ways to detect this activity. And we can, of course, detect water vapor absorption from these planets, but a great way to detect is in the case that these planets don't have atmospheres, which our calculations show that they don't, if they have anonymously high albedos, that will suggest that they have been freshly resurfaced when we look at them through telescopes with bright icy particles from geyser-like plumes. We have more details in Quick et al. 2023, which is being published today in the Astrophysical Journal. Thank you so much for your attention.
Thanks so much, Lynnae. Lovely presentation, really exciting work. Next up of our 4 presenters is Dr. Jon Zink from Caltech, whose title of his talk is Exoplanet Galactic Address Dependence, the Small Planet Decline. Really, really fun stuff. Either way, take it away, Jon.
All right, great, thanks. Get this going. All right, hi everyone. So I'm gonna start off my talk by actually zooming out very, 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 very far. So instead of thinking about planets, I wanna talk about the galaxy for a second. So about 13 billion years ago, the Milky Way galaxy formed out of gas clumps. And we have evidence based on basically the oldest exoplanet we've found to date that planets were forming at this very, very early stage of the Milky Way's formation. So let's fast forward a little bit. a couple billion years later, the thick disk is born. This is a structure in the Milky Way that's about 5 kiloparsecs thick, and it represents some of the earliest substructure of the Milky Way. During this era of the thick disk, there's some interesting stuff going on in the galaxy, and I promise this all becomes relevant with planets in the near future, but during this era, there's type 2 supernovas are occurring. These are the dominant supernovas, and they're producing a lot of alpha elements. These are your oxygen, silicates, neon, magnesium, things like that are really prominent in this era in the galaxy. And this is important because as we know, the Earth is made up of about 75% silicon and oxygen. So these elements that are born really early in the galaxy may be important for creating small terrestrial planets. So fast forwarding a little bit more, a couple billion years later, a large merger event occurs, and this forms the galactic halo. And during this merger event, we have billions and billions of stars coming in and dynamically interacting with each other. Fast forwarding a little bit more, a couple more billion years, the solar system is now born. And so this is the first presence of the sun, and starting to see some planets form around the sun itself. And then the final piece of the galactic substructure is the thick disk. And this is actually where the sun presides today. This is a much, much thinner disk. It's about 1 kiloparsec-ish thick. And it's really just comes out of the settling of the stars and dust over time. And it's really this nice, it really caps off this nice structure we see in the galaxy. So we have a thin disk, thick disk, and a halo. And during this thick disk process, which is a later stage, we have a different type of supernova that's really dominant, and that's the type 1a supernova. This is the where you have 2 stars, you have a white dwarf and a bigger star, and they're interacting in a way that triggers a supernova. And this type of supernova produces a lot of iron. And so we believe iron is a very important facet in the formation of giant planets. So, okay, I gave you this whole overview on how the galaxy came to be, or how we currently think it came to be. And what does this have to do with planets? And the truth is that planets are forming throughout all of this chaos that's happening in the galaxy. So we have lots of dynamics, lots of different element abundances coming online. And these systems are not born in total isolation. There's a possibility that the galaxy itself is imprinting in the planet population and really possibly changing the planets we're seeing. So what our study did is we wanted to look and see if we could look at different features of the galaxy or different substructures and see any changes in the exoplanet population. So this is a tall order. It's not necessarily an easy thing to do. And the reason for that is because we get a snapshot of where the stars are today. But the reality is these stars are orbiting around the galactic center, and they're also oscillating about the galactic midplane. So we need to use very precise astrometry, which is now available thanks to the Gaia mission. And what we can do is we can back out what is the amplitude of this oscillation, because this amplitude tells us something about the substructure classification for these different stellar hosts. And fortunately, we have really good astrometry available, and we can start to do this and dissect these different features of the galaxy and how they may impact our exoplanet population. And here's our big finding. So when we went through and did very careful analysis, we found that as we move up in galactic amplitude, so as that oscillation got bigger, so stars that have larger oscillations, we found that the small planets are decreasing in occurrence. So on this plot here on the y-axis, I'm showing the planets per 100 stars, or the percentage of stars that have this type of planet. And then on the x-axis, I'm showing the oscillation amplitude. So this is how high up those oscillations are happening about the galactic midplane. So stars that are very much in the thin disk seem to have a lot more of these smaller super-Earth and sub-Neptune planets than the stars that oscillate with these really large amplitudes. This is a really strange and surprising finding. It has a lot of complexities to it. One I'll highlight is that there is a known metallicity gradient for the galactic substructures. And we wanted to make sure that that wasn't the only feature really accounting for this. And that's this Fe/H line. You can see that that line is not nearly enough of a decline to account for this massive reduction in super Earth and sub-Neptunes we're seeing. So it seems like a really exciting result. It seems to suggest that the galaxy itself is imprinting on the exoplanet population. And we need to think about the galaxy in a broader sense to really understand all the different planets in our local region. So why might this be happening? There's really only 3 reasons that this could be happening. It's pretty straightforward. One of these 3 is right. It's either system evolution. So given enough time, if say we're looking at maybe an older population that have these higher oscillations, these systems just become dynamically unstable and kick out various planets. Another option is that there's some kind of galactic dynamics at play. So for instance, I mentioned there was a major merger event that gave birth to the galactic halo, and that injected a lot of stars into the Milky Way. Potentially that increased some of the stellar encounters and could have kicked out some of the planets. So that's another possibility. And then finally, it could be that at different times during the galaxy, we have different chemical abundances available. And so maybe there were just fewer planets formed at these earlier stages, causing these higher oscillation stars to just overall produce a smaller number of planets. But the big takeaway is that the planet occurrence rates we're finding are very address dependent, and we can't really take a value that we're finding locally and extrapolate it to the whole galaxy. This becomes really poignant when you think about values like eta Earth. This is the probability of finding an Earth-like analog, an Earth analog. And we often take this value and just kind of extrapolate it outward and say, well, the whole galaxy must have roughly the same fraction of Earth-like planets. But the truth is there's a lot of complexities to the galaxy, and we can't just extrapolate blindly. We have to acknowledge that this is a local value and things may be very different in different parts of the galaxy. I will conclude by leaving up this slide. Very excited that you guys are here to listen, and I appreciate your time. Thank you.
That was excellent, Jon. Thanks so much. So from exoplanets and ice to exoplanets, we are now back to ice. Our next presenter is Pietro Matteoni from the Freie University Berlin. I'm not going to try to say the German name. I'm not that talented. But the title of Pietro's talk is Ménec, Fossae, and Thrace Macula on Europa, hints for shallow water pockets and identification of the youngest terrains. Take it away.
Yes, just 1 second. Okay.
You're good.
Yeah, okay, perfect. Okay, yeah, hi everyone. I'm Pietro Matteoni. I'll talk about our work that we conducted in Berlin in the group of Frank Posberg. Yeah, we studied 2 regions of Europa, Ménec, Fossae, and Thrace Macula. And we will see how this leads to for hints of shallow water pockets in one case, and the identification of the youngest terrains in the latter case. So some background information on Europa is an ocean world that is a body with liquid water below an icy crust or ice shell. And ocean worlds are important because they are the most likely habitats in the solar system for extraterrestrial life in the form of bacteria, for example, or this kind of life, not big aliens, probably. Yeah, some past space missions that visited Europa were the Voyager missions in the 70s. In the 90s, the Galileo mission conducted the most extensive observations on Europa, and this is still the data set that we mostly use up to today. But soon, in a few years, there are going to be 2 missions that will study Europa, and this is the Europa Clipper, NASA mission that will especially focus on Europa, and the JUICE mission here to the right that will study the whole Jupiter Galilean satellite system with a major focus on Ganymede and Callisto. Yeah, so we said Europa is an ocean world. What does it mean? As you can see here, there is an icy crust or an ice shell above ocean underneath. and this is the water layer, the exterior water layer. Then in the interior there is a rocky interior and a metallic core. Yeah, this is another schematic of a similar view of the interior of Europa. And as you can see here below, there are several possibilities for the thickness of this external ice layer, and it's still highly debated, and this has will have many implications for the habitability and the exchange processes between the interior and the surface of Europa. But let's say the ice shell is in the order of kilometers thick, but we don't know if it's 1 or 2 kilometers or much more. So talking about exchange processes, here you see a schematic of the many different processes that may be ongoing on Europa. We mainly know this from the surface expressions that they have at the surface precisely. And therefore, characterizing and studying these processes is very important to understand what's going on Europa, basically. And it's important to note that if biosignators are produced within Europa's ocean, they will need to reach the surface to be detected by space missions. That's why we study all this. So talking about what might be happening in the ice shell of Europa, considering that fractures that directly connect the ocean to the surface are not so likely. In recent years, many studies have proposed the presence of shallow water pockets that you see here summarized in a schematic. So there are liquid water lands or pockets in the very shallow subsurface within the ice shell of Europa. You see here the ice shell and the ocean, and therefore they are critical for the habitability of the Jupiter icy moon. They have been associated with many different surface features, as we will see later in in our results, like double ridges that you see here, or chaos here to the right. And it's important to note that tectonic cracks can emplace material on the surface that might come directly from the ocean, maybe, or from shallow water pockets. So the material reaches the surface through tectonic cracks, and this is also important for what I'll show you later. So going on to our actual study, this is our regional view of our study areas. Study area 1, which I will first talk about, is Ménec Fossae. Here is a small portion of the surface of Europa with Galileo data. See here the scale, 170 kilometers. So study area 1 here to the south, and to the east, study area 2. Now I will go on to the first one, Ménec Fossae, which is an interesting area that displays in relatively small portion of the surface the interaction between different features that are likely related to the subsurface. These features are the chaos terrain here in blue, or in orange, double ridge and a band that takes part of a lot of the map area, and the Fossae here in the middle. So without going into much detail, I can also tell you that we propose that this area has been shaped by tectonic activity in the probably recent past of Europa, and the morphology and the elevation of the area suggests that such tectonic activity likely occurred associated with a shallow water pocket in the ice shell. Now I'll tell you why we think this is happening. Just a few words on the elevation of the area. How do we get this information? Is from this digital terrain model, so 3D model basically of the surface. Now here you see it in 2D, but it basically gives you elevation values of each point map. So then you will see here, this is the data that we get from the DTM. So this is our first line of evidence in support of the presence of shallow water pocket. Here along this line, we trace the profile, and as you can see, there is a series of curves, or in geological terms, folds, that alternate, and this is the expected surface expression above a thickening shallow water pocket. Another line of evidence is provided by the elevation values here to the north along the double ridge, well, across the double ridge actually. And as you can see, these are our observations, and they match perfectly with the expected features that have been proposed in a model some years ago that will support the presence of a shallow water pocket underneath a double ridge when these features are present, and we see all of these features in our area. And ultimately here in the very north, we have the transition between the chaos and the related like surrounding terrains, and the down drop elevation of the chaos is also in support of this hypothesis. Now I will move on to study area 2. So Thrace Macula, which is here in darker color, is known to be a young terrain, and there is already known presence of material originating from Europa's interior, and this makes it a prime target to investigate the astrobiological potential of Europa. And in fact, JUICE and Europa Clipper will study it in detail. It is already planned. So I'll focus on the southern part of this study area. We think the interaction between Thrace Macula and its surroundings, in this case is Libya Lynnae, which is another very big structure, is characterized by a tectonic fault. And here you see the acquisition time of the data, and we reconstructed the movement. I'll show you a couple of times. This is what we see, and this is before the imposition of this fault, and we think this matches almost perfectly. So this proves the fact that there was a fault that moved the southern part of the image. So for those faults that form after Thrace 1, such as formed after Thrace, such as fault 1, which is this fault I just showed you, they can act as conduits for fluids. So deep material from Thrace can infiltrate along them and then place on the surface. And it's important to note that surface material needs to be young to be astrobiologically relevant on Europa, because the rest is altered very quickly by radiation from Jupiter. And we think that we identified the youngest material in this portion of the surface that is related to Thrace, that can be encountered and assembled by JUICE and Europa Clipper in this area, and this terrain is here highlighted in the white dashed line. So just to summarize very quickly, our findings in the case of Ménec Fossae suggest the presence of a shallow water pocket and have implication for our understanding of Europa's ice structure. And in the case of Thrace Macula, lead to identify the youngest and most astrobiologically relevant terrains in the area. These results have been published this summer in July and August in 2 different publications, and I give you the link, and thank you very much.
Thank you so much, Pietro. Successfully. Oh, no, I'm unmuted. Yeah, thanks so much, Pietro. I've successfully done my job as a DPS press officer, and then I've gotten galactic dynamics and geologic modeling into the same talk. Last but not least is Dr. Gordon Kai-Hu from the University College London, who you can get ready to start sharing your screen. The title of Gordon's talk is The Ariel Data Challenge. What can we learn from outsourcing our problems to the AI community? Can you mute yourself? Yes.
Thank you. Thank you, Teddy, for the introduction. So hi, everyone. I'm Gordon. I'm actually the PI of the Ariel Data Challenge. Here I'm talking on behalf of the entire organizing team. So before I talk to you really about the data challenge, let's zoom out a little bit and think about what we've done really. So in the past 10 years, what we know about is that exoplanets are ubiquitous. They're everywhere. And there are questions that we've been asking them, like how do they form? What are exoplanets made of? Are any of them habitable? We start getting answers about this, but we are very far away from having really a conclusive conclusion about that. But these are really high priority questions in the NASA Decadal Survey. And this is also reflected in NASA or ESA's missions on exoplanets. Here we have, at the start of the 21st century, we have detection missions. But then beginning on 2019 with Cheops, Webb, Roman, and in the near future, Ariel, we're looking at characterizing exoplanets. So the focus has shifted slightly from detection to characterization. And together, this mission will provide observation of thousands of planets. So why are we doing the Ariel Data Challenge? Well, first of all, we need to come up with a solution to deal with a lot of this data. And the second one is building a mission and problems within the mission. They're big challenges. We require a community of researchers from different backgrounds to help us with that. But the problem is, scientists don't really speak the same language, even though all of them speak English. If you look into a computer scientist journal or astrophysics journal, they have their own jargon. So here really is that when we create the Ariel Data Challenge, we want to create a platform where they can actually come together and crowdsource solutions for these kind of big problems. We've been doing this for 4 years now, and each year we partner with a major machine learning conference. In 2022, we actually partnered with Lynnae, one of the most prestigious machine learning conferences in the world. And really, just every year we explore different issues in planetary science. And in our last 2 years, we've actually reached over 300 plus participants all over the world, and over 50% of them are coming from Europe, UK, US, and Asia, such as India and China, but also with 30 plus other countries as well. So what's the content of this challenge? Is that given an observation from Ariel, you can think of it as, from James Webb as well, can you predict the atmospheric properties of that exoplanet? Just that question. And the lessons that we learned, the first lesson is machine learning models dislike surprises, but space missions are specifically designed to explore them. How do we arrive at that conclusion? So here's a plot where we have our top 10 participants on the x-axis, and on the y-axis is the score they got. So the higher it is, the better. The blue curve is their performance when the training data is the same as the test data. And they experience a systematic decline in their performance when the machine learning model is exposed to data that is outside of their training data. So we saw that in 2022, and we thought, okay, we are scientists, we have to repeat the whole thing again and see if we got the same result. And we did. So in 2023, we got the same result where, again, the blue curve is when you have the same training to the test set. But then for the rest of them, the red, green, and orange, they are basically having a completely different atmosphere to the training set. And then the machine learning model doesn't like it. They can't really outperform. And this issue is formally known as data drift in the machine learning literature. What's the significance of all this? Well, despite the hype with AI right now, there are major obstacles ahead before it can be really adopted to space science to missions, because space missions are built to explore the unknown. But many machine learning models become unreliable when facing this. And the reason why we can say many is that we've got 50 teams, 100 teams all around the world doing these problems for 2 months, 3 months on the same data set. So in a way, it's the first kind of large-scale social experiment conduct to sort of explore this vulnerability. What's the second question? A second lesson. It's a confirmation that money is important, but at times, so is passion. So we look at the number of active teams in Neolibs 2021 to 2022. So that's basically the top 15 of them. We look at the number of participants. So we've got to 5th place. It's not too bad. But if you look at the price that we've got it, we've got 4,000 as the price. Whereas some others have got 20,000, 200,000. So we thought like, okay, there must be another way of seeing this. So we actually look at the way how efficiently those money are spent. So for every pound or every dollar you spend, how many participants can we attract? And we got the 3rd place. And so we're thinking, oh, actually, maybe science really matters. The passion really matters. But we want to confirm that. So we ran a survey to all the participants and asked them, why are you interested in joining our competition? And the result confirmed what we thought, is that they are interested in the problem, the machine learning problem, but also about the science of exoplanets. The price, well, not so much, as you can see on the far right. Now, for the last lesson that we've learned is that physicists are required to win the game. So even with all the ML pipe that we around us, we do need physicists in order to win this game. What are the common? So these are the winners of throughout 3 years of the Ariel Data Challenge. What's the common from between all 3 of them? All of them actually have background or team up with astrophysicists to actually win the game. So what is shown is that we need physics knowledge in order to understand the problem, in order to really give a solution that can win the game. So I'm just going to give you a summary of that. Is that challenges tomorrow really requires a focused effort, not from astronomers, but from everyone else. But it takes a lot of effort to really engage a different community, but the reward is huge. So the Aero Data Challenge aims to crowdsource a solution to a significant space problem. And the lesson that we learned is that data drift really poses a challenge when applying machine learning models to missions data. And the second one is that the community is eager to engage, even if the price is somewhat small. And the final lesson is that the physics is essential to develop a winning solution. Thank you very much for listening to my talk. I'm really eager to hear about all your questions. Thank you.
Okay, thanks so much, Gordon. All right, all of the participants at today's press conference can turn their videos back on. We'll do a little Q&A session. For those of you who are watching online, I will remind you, you can put your questions in the Zoom Q&A and we will read them out, but I have some pre-prepared ones we can use as people are thinking through their thoughts. And if anything comes up, just put it in there. You know, there's no stupid questions, there's no wrong questions. But if you're not answering a question, if you could keep yourself muted just so we don't have any more crosstalk. I think that last one was my fault though. I'm trying to pretend it's not. So for Lynnae first, one of the questions I had thinking about your really exciting talk was, you know, we're trying to extrapolate something about what we know about our solar system to lots of other ones, right? And I was wondering what kinds of things you would want to know about, for instance, Europa or Enceladus that might allow you to, you know, think about, for instance, an even better exoplanet telescope proposal, the next steps in your research. You know, what are the current things that we don't know that might help what you want to do?
Sure. I think Pietro hit on a lot of those notes, those things that we would like to know. We know that we have surface subsurface exchange on Europa, meaning that, as he mentioned, we know that we have fluids that from the interior that come to the surface, but we're not exactly sure how that happens. So basically the subsurface plumbing on these icy moons, whether we're thinking about Europa or Enceladus, and how the differences in thickness in their ice shells play a role in what comes to the surface and what erupts out of it, and what cycled between the surfaces and interiors. If we have, as he mentioned, Europa Clipper that'll be launching next year, and Juno that launched this year. And so the more that we can constrain about the ocean worlds in our solar system, the more we'll be able to extrapolate when it comes to cold ocean planets. Yeah, thanks.
Yeah, sweet. So for Jon, you were talking about how sort of, you know, in addition to the sort of, you know, place in the galaxy dependence on the what kinds of exoplanets are forming, you'd also mentioned that, you know, exoplanets have still been forming the whole time, right? You know, you form the galaxy and the exoplanets start showing up quickly. I was wondering, you know, in addition to you know, what you were talking about in terms of, you know, the exoplanets that form with around these higher amplitude stars, maybe there's less of the small stuff. How do these earlier planets compare to, you know, the ones that are still forming today? Are these completely different populations as well, or are they, you know, something we can kind of model and understand?
Yeah, it's kind of unclear at this point. We don't have quite enough of a sample to make a strong statement on that, but I will say, looking at like the younger side of the population, so I focused a lot on the older side, but if you look at the younger side of the population, we have a lot of mechanisms that have to do with like mass loss that can kind of expel the atmospheres of these planets. So what we find is a lot of the younger systems have more larger planets with larger envelopes, so larger radius planets with like a fixed mass. So it seems that given enough time, these envelopes kind of erode, and there's some inkling of evidence that this has like a long-term effect as well, so that this erosion never really truly stops and it just kind of tapers off at some point. And so one of the things we're looking for in the future is hopefully we can see if there's any mass loss on a very like, you know, billion-year time scale or anything like that, rather than the million-year time scale that it's currently being studied at.
Perfect, thanks. Pietro, who I'm going to pretend is not sitting across the room from me. One of the questions I had from you is, you know, you've identified these really young terrains, right? And, you know, these might not be, you know, like exactly in contact with the ocean, but they're in contact with some part of the interior. And I was wondering what your work, what the identification of these really young terrains tells us about that deep interior, sort of outside of the life stuff. You know, I know I'm supposed to be focused on the life, but, you know, what does this tell us about the ice shell? What does this tell us about, you know, how the interior of, you know, Europa works?
Well, let's say first to really understand how the interior of Europa works, I think unfortunately we will have to wait a few more years when Clipper and Juice are going to be there, because so far I mean the data set is really limited. But let's say what we can say right now is I mean all of this work now is needs to be done in preparation for this mission. So then we can say, okay, you have to go there, like, because you know these missions have not unlimited flybys. Everything is very constrained, and so what is important right now is like to say where is the in this case we can say it in a very limited space constraining, like we can say you have to go there, not 10 kilometers away, and then we will be able to answer a bit more how the ice shell of Europa works, because at the moment the data set is very limited. It has been squeezed already quite a bit.
Yeah, I guess Europa is getting squeezed all the time by Jupiter too, right? Sorry, that was my one little fun joke. Gordon, I thought you had a really exciting talk, and I think that this project to understand how well machine learning can work in these kinds of techniques is, I think, really interesting for lots and lots of reasons, right? I was at some point sort of happy to know that the machines can't quite do it yet, right? That the machine learning can't handle these surprises in a way that spacecraft, new telescopes, new techniques just seem to pump out. Are there, sort of different techniques on the horizons, or different techniques that you think might be a little bit better suited to being able to handle, the kind of variety that shows up in a real data set from a real space telescope, from a real spacecraft?
Well, on the horizon, I'll say I'm actually on that because I'm space mission are sort of like, you have to be robust, you have to be really safe. So I'll say I'm on conservative side, even though I'm really excited about the prospect of machine learning really bring to us. But I'll say for now we'll be exploring our conventional techniques and see how actually, instead of replacing the whole thing with machine learning, which we were trying to do here, is actually can we actually complement them, like replacing small bits of them, instead of really just say, okay, let's throw away the old stuff and just get in the new stuff. Yeah, that would be what I think.
I'm glad we're not in like the Terminator 2 situation yet. Lynnae, I was interested in sort of, some of the testabilities of these different things. You were talking about that if these things are icy worlds and they're like the icy worlds in our solar system, you'd expect them to be bright, surfaces that are icy, if they have cryovolcanism or they're spewing stuff on the surface, this is going to keep them shiny, bright, reflective. Are there particular exoplanets for which we could test this sooner than others, or is this a kind of next generation technology kind of question that we're going to have to wait for the next round of big new investments?
I think if when it comes to indirect detection, I think for some of these exoplanets, we can maybe look now. There have been a lot of studies on when we think about Proxima Centauri b and some of the Kepler planets. And so when we look for bright icy surfaces, as you mentioned, that's indirect detection of cryovolcanic activity. But when we think about one of the points that was on one of my slides that I didn't have time to get into, when we think about actually detecting water vapor absorption from these exoplanets as it's being lofted into space, we're definitely going to need some next generation telescopes to be able to get that, even in cases where the water vapor that's outgassed is orders of magnitude greater than Europa's. We have to remember that these planets are still orders of magnitude bigger than Europa, and so you are definitely going to need much higher powered telescopes to detect this activity directly.
Cool. For Jon, I have another sort of question. I think this one is going to require you to put on your speculation hat. So, this is me warning you. So, one of the things that you found out, through this study is that these, high amplitude stars are producing fewer of these smaller planets. And the question is, I know that there's, 3 different hypotheses you lined up for, processes that could be playing a role in this. do you think that the small planets they're forming, do you think these are still sort of like the small planets that are forming around the lower amplitude stars? Or do you think that, if you got a group of one and you group of the other, they might look kind of different? Maybe this is composition or size or structure or orbit, or I guess I'm sort of asking, like, do the same things happen in the same order, the same way? Or, does the difference you've identified sort of propagate everywhere?
Yeah, it's a very interesting question. You're right. We certainly don't have enough data to make any claims quite yet, but is it possible that you have these system dynamics playing out in a way that you form similar planets, but they're made of different compositions? And I think that's very possible. It will be very interesting once we get more atmospheric information from, say, JWST and what many of the other speakers have discussed today, to see how the compositions compare in these different regions of the galaxy. I don't know. It's really hard to say. There's been a lot of work to look at alpha elements and see if there's some kind of correlation with planet formation and alpha elements. And truthfully, our finding kind of goes against that in some sense. The expectation was that as you go higher up, you would have higher abundance of alpha elements, which are expected to kind of seed terrestrial planet formation more likely. We're finding the opposite is true, that there's fewer small planets, kind of contradicting the expectation of this alpha element propagation of small planets. So yeah, it's a pretty weird finding, and I just don't know if we know enough about how planets form, what compositions are important, how opacity plays into all this. It's just a complex system with a lot of knobs to turn. So yeah, to be determined.
Yeah, there's a follow-up question from the Q&A, which I'll just ask you now while you're still unmuted.
Okay.
So you mentioned that one of the three potential scenarios that might explain some of your observations, or your conclusions, right, is changes in the composition of the disk, or changes in disk composition. The Q&A speaker asks, could it also, or rather, be a change in the disk initial masses, depending on sort of the original neighborhood, the original place the star grew up, for these systems?
Yeah, that's a really great question. Yeah, I should be more general with my statement. It just has to do with the disk in general. But yeah, it's very possible that you can have a star that has a disk, and maybe this disk got stripped away in some sense. So if you have a higher density of stars and say like a globular cluster, there's a greater likelihood that you're either going to strip the disk or you're going to evaporate the disk because you have these really, really massive and powerful O stars that are just kind of blowing away material. So yeah, anything that can change the disk in these different regions would certainly cause this deficit in planet occurrence.
Sweet. Okay, I'm going to try to get one more question to our other two speakers, and then we're going to start hitting the clock. For my colleague across the room, Pietro, I think there's this sort of the elephant in the room with Europa sciences that, we're sending a big spacecraft there, right? And then there's going to be spacecraft exploring the other icy moons in the same system, right? At some level, the future is going to change everything, right? We're going to know so much more about so much more. I was wondering, when Clipper gets to Europa in a couple of years, do you think that these are going to stay the youngest terrains, or with new techniques, with new ways of thinking, are we going to be able to find even younger terrains and, even more, sort of like close to the water, spots on the surface? Is sort of is the future bright for, finding even. I was trying to use bright as a joke here. I messed up the joke. I'm trying to say, like, what do you think Clipper is going to find in this area? Do you think that they're going to find something even younger? I'll cut myself off.
Yeah, thanks for the question. I mean, let's say, also maybe I have to answer in more detail your previous question. That is, so Europa is, these results prove that Europa is very active, or at least has been very active in the recent past. The recent past in geological terms is 100,000 years or 500,000 years. So this also answers your actual question. So in the span of 10 years, this is still going to be like a baby terrain. Like that will, well, if we see that it has changed, this is will be a big news. But within 10 years, probably the changes at the scale of the observation are not gonna be a lot. And but of course, then Clipper will have a much higher resolution. I mean, also, I don't remember right now the total percentage of the surface of Europa that has been imaged by Galileo, but is not so much at interesting resolution, and Clipper and JUICE will do this on a much larger extent, and we will know, let's say, we will find out about other terrains that we don't know they exist yet, and they will probably be very young, but let's say then we can apply the same techniques that we are applying right now to find out more about Europa.
Okay, cool. Thanks. I guess go Clipper. That's how everyone feels at the DPS anyway. It's not really, it's almost like something you don't even say anymore. For Gordon, one of the last bullet points you had, and I think this will be the last question we'll have time for. One of the last bullet points you had is, that actually building the right models and actually interpreting the data correctly, you couldn't just be really good at machine learning, right? You really couldn't just be an excellent programmer. You also had to understand the physics. You had to understand the problem itself. Do you think that, the workshops you've done, the questions you've asked, the things you've heard from people, do you think you've learned something sort of about how to, build the right team for this kind of process, right? Do you think that, we're learning something about how to best use, in this case, really, advanced and exciting new sort of data analysis techniques like machine learning and incorporate them into sort of ongoing research? Do you think that you've gained some insight into how to best do that?
Yeah. I think we've got a lot of insight into how to really build this kind of, but the first thing that we learned, actually, one of the things that we actually asked before we organize this competition is, do we really need physics? Can machine learning programmer just replace us? That's it. You just need to be really good at machine learning, have a really fancy model, and that's it. But we know you do need physicists. We do need physicist input. And I think one of the things that we learn is how to really communicate between the two parties. Chances are you've already they know how to solve the problem if you can communicate your problem accurately. But these are jargons, astronomers have their own jargon, and then computer science, they have their own jargons, and then I think the first really major lesson is how do you communicate between both parties.
Well, great. With that, I'll say that this press conference is over. I'd like to say thank you so much to each of our 4 excellent presenters today, and I want to say thank you for all the hard work they did to prepare to learn how to, talk about the cool work they do and talk about it to you. I want to say thanks to Susanna, Carrie, and Ben over at the AAS, and I want to say thanks to all of you who are watching this live or were watching this, a couple hours from now, a couple days from now, a couple of weeks from now. If you have any questions for any of these presenters, you should certainly feel welcome to reach out to me, and I can certainly pass along your questions or put you in direct contact with them. The most important thing here is that the public gets to know more about the cool work that the people at the DPS and the EPSC are doing it. With that, I'll say